Hello, and welcome to Lesson 9 of this Introduction to Calculus with Wolfram U. Our topic for today is differentiation formulas. So let's begin with a brief overview of today's lessons. The point is that one can find derivatives using the limit definition, but in practice, this is quite a tedious and tricky approach, and one wishes that there was some simpler way of finding derivatives in practice. And luckily, there are formulas which help us to find derivatives of many commonly occurring functions. So, for example, here is a constant function f of x equal to c, and you can see over here that the derivative of this function is just 0. So the derivative of a constant function is always 0. Let's check the graphs. So here is a graph of the function, and the derivative is 0. So in this lesson, what we'll do is we'll cover basic differentiation formulas of this type, and by the end of today's lesson, you'll feel quite comfortable about computing derivatives in practice. So as a first example, here are the power functions. So your function x raised to n, so for different values of n, you get different power functions. So taking this function and finding its derivative gives you n times x raised to n minus 1. That's a very well-known formula in differential calculus. So for example, if n is 2, then you have a quadratic function, and its derivative is just 2x. So it might be good to memorize that the derivative of x squared is 2x. And let's plot the function and derivative. So that's the function, a quadratic function, a parabola, and that's the derivative. And clearly, the derivative must be negative on the left because the function is decreasing. So slopes are all negative over here. So to go on to the same topic, suppose you have x to the negative 1. That's a negative number, but the same rule applies, and you get back negative 1 over x squared as the answer. So again, here's a plot of the function and its derivative. And finally, let's take an example where you actually have a kind of negative decimal power, but the same formula applies, and you get back the derivative in the same form, n times x raised to n minus 1. Okay, so to go further, let's now talk about constant multiples of functions. Here you have a constant and a function, and when you try and find derivative, what you do is you simply pull out the constant from the function and find derivative. So the derivative over here is just 15x squared, which is 5 times 3x squared. So the 15x squared over here is the constant 5 times 3x squared, which is the derivative of x cubed. So here's a plot of the function derivative, and you can see that this is a very simple rule, the constant multiple rule. So to go a step further, let's look at a very important rule, namely the sum rule. So if you have a function f and a function g, and you find their sum, then the derivative of the sum is just the sum of the derivatives. So you simply work out f prime and g prime separately, and then when you add them up, in this case you get back 6x plus 2, which is the correct answer. So the sum rule makes it quite simple to find the derivative in such cases. So once again, here's a plot. So you have the function f of x, the function g of x, and the derivatives over here are f prime x, g prime x, and the sum has got derivative, which is the sum of those two. Okay, on to the difference rule, which is very simple and similar. So if you've got a function f and a function g, and you define the difference, then the derivative of the difference is the difference of the derivatives. Namely, you work out f prime x, work out g prime x, and then you subtract them, and you get back the answer for the difference derivative. Here's a plot of all the derivatives. So once again, you see that if you have a difference, then the derivative is really simple to compute. So sums are simple, differences are simple. Question is, what happens to products? Well, if you have a function f of x, another function g of x, and you multiply them to get the product, you might think that the derivative of the product is the product of the derivatives, but that is not the case. In fact, if you work it out over here, you get square root of x in one case, and you get quite a different answer in the other. And it turns out that in this case, the correct formula is you do f times g prime plus g times f prime, and then you do get back the correct answer for the derivative of the product. Once again, here's a plot of all three derivatives to give you a feel for what's happening over here. But notice that now things are no longer simple. You actually do need to memorize a rule which says that the derivative of the product of f and g is f times the derivative of g plus g times the derivative of f. And if that is not complicated enough, let's look at the quotient rule. So if you have f and g and you take their quotient, so you divide them, then once again, the derivative of the quotient is not the quotient of the derivatives. You can check that over here. If you do f prime over g prime, you get one answer. If you find a derivative directly for the quotient, you get another answer. And the fact is that the quotient rule for derivatives is a lot harder. It says that the derivative is g times f prime minus f times g prime over g square. So in this case, the rule gives you the correct answer, namely negative 3 over 2x cubed. Once again, you can plot all the derivatives, and you learn that the quotient rule is significantly more complicated than the earlier rules, but in fact, it does give you the correct answer in all cases. So we've learned the sum rule, the difference rule, the product rule, and the quotient rule, and in fact, that brings us to the end of today's lesson. So the point is that yes, derivatives are useful, but it is only when you have the rules for differentiation that you can actually use them effectively in practice. So you do need to know all the rules we learned today. So there are rules for sums, differences, products, and quotients. And of course, the simplest rule is the power rule, which lets you find the derivative of things like x squared and x cubed and other powers of x. So in the next lesson, we'll go on to doing something more with derivatives, namely talk about the trigonometric functions. But before we do that, do make sure you reviewed today's lesson, try the exercise, and make sure you're ready for the next theme, which is the derivatives of trigonometric functions. So I stop over here. I hope you found this lesson really useful. This is where calculus really begins, where it becomes a very algebraic kind of process and becomes easy to apply in practice. So thank you very much. I'll stop over here.